You've likely bumped into the Pythagorean theorem before. Some pretty fundamental stuff.
Yeah, definitely.
But today, we're not just dusting off that old formula. We're really aiming for a proper deep dive, trying to properly get it.
Absolutely. Because often we just learn it as a tool, right?
Yeah.
A way to calculate a missing side on a right triangle. But the sources we're looking at today, they offer something, well, much more intuitive, almost like a story to help understand it.
A story? Interesting.
Yeah, the goal is to see why that equation actually works, not just how to plug numbers into it.
Okay, I like that. And you mentioned sources. We've got a YouTube video using a farm. That sounds different.
It really is a farm analogy to visualize the theorem.
Yeah.
And after that, there's this cool hands-on tool, a bead simulation called the Pythagoras.
The Pythagoras. Yes.
Okay.
So our mission then for this deep dive is to use these kinds of engaging methods to really see the theorem in action in a way that hopefully properly clicks.
Exactly. Let's head to the farm first. This Pythagorean farm video. Tell us what's going on there. What does it look like?
Okay, so picture this. You've got a farm, right? And there are 4 tenant farmers.
Mm-hmm.
Each one has a rectangular plot of land, but it's cleverly split diagonally into 2 triangles.
Okay.
One triangle's for farming, the other's for grazing. And smack bang in the middle of all these plots, there's the shared grazing area and a pond.
A shared space.
Yeah.
Got it. And these rectangles,
Yeah.
they must relate to the A, B, and C, I'm guessing.
Exactly right. The video points out the shorter side of each rectangle is A, the longer side is B, and that diagonal line splitting them, that's C.
Ah, the hypotenuse in this visual.
Yep. And here's the really key bit. That central share area, the grazing land and pond, which is bordered by all those C diagonals.
Okay, so the central square is C squared. That's like visually putting one piece of the puzzle right there in the middle.
Precisely. It sets up the theorem visually from the start.
Yeah.
It's not just about the lines, it's about the area of the square on that line C.
Right. It's about the space. And who's running this farm? You mentioned tenants.
Yeah, there's a landmaster, the owner. He's got his own plot, upper right, apparently. And his job, well, it's to oversee the tenants, check their crops, and collect his rent, basically. A share of their harvest for using the land and the water.
Okay, so he's part of the story too. How does he fit into demonstrating the theorem? What does he do?
Well, the video shows this scenario.
Yeah.
The landmaster goes around counterclockwise, visiting the tenants.
Okay.
And when he gets to the last one, this farmer hasn't grown enough. He's short on his rent, basically.
Ah, okay. So there are consequences.
There are. The landmaster takes some of this tenant's land as payment.
He just takes it. And what's left for the poor tenant?
What's left is just a small square plot of land. And crucially, the video makes it very clear. This remaining square, its area is A.
A squared. Okay, so we literally see the A squared emerge from this interaction. The square on the shorter side.
Exactly. You can sort of see the pieces coming together in the story, can't you?
Yeah, you can. So that's A squared visualized. What about B squared? How does that show up?
Well, this is where it gets quite clever. The video explains that if you think about the whole farm area relative to that central C watering land, the landmaster effectively controls an area equivalent to B.
How so?
It's his original plot plus the land he just took from that tenant. That combined area visually represents B.
Okay, wait. So A is the bit the tenant has left, and B is the landmaster's total holding after taking some land.
That's the idea presented. Yeah, we're seeing these areas defined on the farm.
Okay. So how does this all connect back to that central C area, the pond and grazing land?
Right. This is the visual payoff. Remember that C area is bordered by 4 yellow triangles.
The diagonals formed those borders.
And remember, each tenant's rectangular plot was made of 2 identical triangles. So those 4 triangles bordering the central C area, they represent the area of 2 whole rectangular plots. 2 lots of A times B.
Ah, okay. Because each AXB rectangle is 2 triangles. So 4 triangles equals 2 rectangles. Got it.
Exactly. Now here's the connection the video makes. It shows that the central C area is equal in area to those 2 AXB rectangles plus the actual watering square in the very middle.
Okay. CY equals 2 rectangles plus the inner square.
And then it shows that if you take the A area, the tenant's small square, and add it to the B area, the landmaster's combined holding, that also visually equals those same 2 rectangles plus the watering square.
Whoa. Okay. So visually, A plus B occupies the same sort of space, the same component areas as C.
That's exactly it. You see that the 2 sums are composed of the same visual parts. It's not algebraic manipulation, it's rearranging areas on the farm. Pretty neat, eh?
That is neat. It's showing the relationship of the areas, not just saying the formula. Okay, get the farm visual now. But you said there was another tool.
Pythagorean. Yeah, the video introduces this too.
Yeah.
It takes the visualization idea and makes it more like a hands-on simulation with beads.
Beads. Okay, how does that work? Like an abacus for Pythagoras.
Sort of. Imagine a square grid of beads, let's say 4x4. That whole square represents, again, a square of farmland.
Right.
Then columns of these beads can slide apart to show those rectangular plots. So in the example they use, the short side A might be represented by just 1 bead's width.
Okay.
And the longer side B by 3 beads width. So you see a 1x3 rectangle made of beads.
So you can physically see the A and B dimensions. Makes sense.
Yeah.
How does it show the theorem?
Well, the simulation lays out these bead rectangles, right? And then, like in the farm story, the landmaster figure comes along to check on that little A square, the 1x1 bead square in this case.
Same story beat.
Yeah.
Yeah.
And when that happens, there's this visual transformation. The beads representing the 4 triangles and the 2 rectangles, they all kind of slide and rearrange themselves.
They rearrange into what?
They snap into new shapes. They become a 3x3 square of beads.
Which is B squared, since B was 3 beads.
Exactly. And a separate 1x1 square of beads.
A squared.
Right. So you literally watch the area that was previously configured in relation to C square just morph into a distinct A shape and a B shape right next to each other.
Wow. Okay, that's direct. You're seeing the area physically conserved but changing form. That feels much more powerful than just symbols on a page, doesn't it?
It really does. You see the equality happen. Take a sec to picture those beads clicking into place. From the C-related layout to the A and B squares.
Yeah, that's a strong visual. It makes the whole idea of squaring and adding areas feel really concrete, tangible.
Absolutely. And the video even notes you can use this simulation to look at other proofs of the theorem too. So it's quite a versatile little tool.
Very cool. So, okay, we've got the farm story and the Pythagoras beads. Both sound like really creative ways to show the theorem instead of just stating it. Mm-hmm. Now that we've kind of explored how they work, let's dig into what our other sources say about how effective these kinds of approaches actually are for learning. Do they work?
Right. Good question. We have these other sources, the effectiveness of the approach and the visual and narrative learning approach ones. They kind of analyze the whole method, the pros and cons.
Okay.
So what are the big positives they identified? What are the strengths?
Well, the number one thing seems to be the focus on conceptual understanding.
Right. The why.
Exactly. Both sources really hammer this home. Mm-hmm. These methods aren't just about memorizing A plus B plus BC. They're designed to show why it's true by connecting it to the idea of areas.
Which hopefully leads to deeper learning, better retention maybe.
That's the idea. If you understand the underlying principle, it sticks better than just a rule you've memorized.
Makes sense. What else stood out as a plus?
Engagement is a big one. Let's face it, a story about a farm or playing with virtual beads is probably more captivating for a lot of people than staring at equations.
Yeah, probably.
The farm gives it context, makes it relatable. Especially maybe for learners who connect better with stories. How about you? Does a story help things stick?
For me, yeah, often it does. And it definitely caters to different learning styles, doesn't it? Like I'm quite visual. Mm-hmm. So seeing something like the Pythagoras beads move around, that would likely click better for me than just abstract symbols.
Precisely. The forces point that out. Improved accessibility for visual learners, or maybe folks who find abstract algebra a bit intimidating.
Yeah.
Breaking it down into these visual chunks, these squares and areas, can make the whole thing feel less daunting, you know?
And it constantly reinforces that core idea, doesn't it? That it's about the relationship between the areas of the squares on the sides, not just the lengths themselves.
Exactly that. It's about the space.
Yeah.
And the Pythagoras gets praised for being dynamic, too. It's not just a static picture. You see the transformation.
The beads moving. Yeah.
That visual shift can be really powerful for understanding how A, B, and C actually relate. Makes the abstract idea of squaring feel more, physical.
Okay, so lots of positives. But I assume it's not all perfect. These sources probably offered some balance, right? Any potential downsides or weaknesses mentioned?
Oh, definitely. They provide a balanced look. One potential issue they raise is what you might call an abstraction gap.
Abstraction gap, meaning?
Meaning, while the farm story is a great starting point, some learners might struggle to connect that specific farm scenario back to the general theorem that works for any right triangle.
Ah, okay. So they might get stuck on the farm details.
Potentially. You need to make sure the story serves the math rather than, accidentally obscuring it.
That's a fair point. Anything else?
Well, related to that, maybe the complexity of the analogy itself. For some students, maybe the whole set of tenants, landmaster, rent, might just add extra layers of stuff to track.
Instead of simplifying.
Right. It could, for some, actually distract from the core mathematical relationship. Kind of begs the question for the learner. Is this story actually helping me, or is it just making it more complicated?
And the Pythabacus relies on tech, obviously.
Yeah. That's another point. Reliance on technology. If you don't have access to the simulation, that tool isn't helpful. Accessibility is always a factor.
True.
And finally, there's a mention of potential oversimplification. Visual tools are great for getting the basic idea, but you need to be careful not to lose some of the mathematical nuances in the process.
Making sure the visual doesn't hide some of the deeper stuff. Okay.
Exactly.
So, given those potential pitfalls, how do the sources suggest we make the most of this kind of visual narrative approach? How do we maximize the good bits?
They give a few key recommendations. One big one is practice. You still need to apply the theorem to lots of different problems.
Makes sense. Abstract ones, real world ones.
Right. That helps you generalize the concept beyond just the form or the beads. You see, it works everywhere.
Okay, so don't just rely on the visual intro. Practice is key. What else?
Integrating these tools with, let's say, more traditional methods. It shouldn't be just the story or just the formula. Use them together.
A blended approach.
Yeah, exactly. That way you cater to different learning styles and build a more rounded understanding. And one more thing.
Yeah.
Encouraging learners, encouraging you, listening, to explain it back in your own words.
Ah, the teach back idea.
Kind of connecting the visual you saw, like the farm or the beads, with the actual symbolic equation, A plus B OS B city. That step, explaining it yourself, is seen as really vital for bridging that gap between the concrete visual and the abstract math.
So use the cool visuals as a starting point, a way in, but then build on it with practice, traditional methods, and self-explanation to really lock it in.
That sums it up perfectly. These methods provide a powerful intuition, a strong foundation for why it works, which then supports the more formal math stuff.
Okay, great. Let's try and crystallize this then. What's the main thing you, our listener, should take away from this deep dive into Pythagoras via farms and beads?
I think the biggest takeaway for you is that the Pythagorean theorem isn't just some dry formula you memorized years ago.
Right.
It's actually describing a really fundamental, quite beautiful relationship between areas. The area of the square on the longest side equals the sum of the areas of the squares on the other two sides. Always, for any right triangle.
And seeing it through a story like the farm or a simulation like the Pythabacus, that can give you a much deeper, more intuitive feel for why that's true. Maybe make it stick in a way it didn't before.
Exactly. It moves it from just symbols to something you can almost see and manipulate in your mind.
So maybe next time you see a right angle somewhere, a corner of a room, a sail on a boat, whatever, pause for a second. Think beyond just the lengths. Imagine those squares built onto each side. Picture their areas. How do they relate? It kind of shifts how you see it, doesn't it?
It really does. And maybe that leads to a final thought for you listening out there. Think about other abstract ideas you've come across. Could be in math, science, philosophy, anything. Could a creative visual approach, or maybe framing it as a narrative, unlock a deeper understanding for you? Like we saw with Pythagoras today. Makes you wonder how many other complex ideas could be illuminated if we just found the right story or the right picture to represent them. Maybe try thinking of one now and how you might visualize it.